welcome to this Smart Grid Basics to Advanced Technologies, and we will be focusing on optimal sizing and siting of storage devices. During the previous lectures, we have seen that energy storage devices are quite important in the field of power engineering. However, after understanding their chemistry, technologies and its modeling part, now the next step would be what would be the size and the location of those devices to be deployed. It is quite important because depending upon the locations, the performance of the battery storage can change, and also we need not spend unwanted expensive devices, or we need not procure unwanted capacity for the energy storage for the field deployment. So, you have to be very careful because each kilowatt cost you heavily. So, we need to be careful before we finalize the size of the battery, whether it is 10 or 20 kilowatt, the location, whether it is substation A or B, that need to be finalized before its deployment. So, how do we do that? We need to do rigorous mathematical analysis to understand or to identify the optimal locations and its size for experiencing or taking the maximum benefit out of a storage deployment. So, let us focus and continue our discussion today in this order. A general ESS allocation algorithm, we will try to understand how this allocation algorithm can be developed, what are those essential parameters, ESS integration, comparison of solution methods, case study. We will try to take a small power system which is of 33 bus and try to understand its process. Again we will formulate the problem and then input data to this algorithm and its final results. Now, when you talk about general energy storage system algorithm, allocation algorithm, so these are the steps one need to follow. So, let me start from the beginning. I request everyone to concentrate. Identify the application to be served necessary network support to be provided by energy storage system. That means, we need to identify the application to be served necessary network support to be provided by energy storage system. So, first of all we need to be clear what kind of application we are looking for. Okay. Is it for deferring the investment, or it is related to a frequency response, or it is related to congestion management, whatever it could be. So, first of all we need to know why we are going for this technology, is it necessary or not. So, once you are convinced about this technology as well as the application, then you have to formulate an optimization problem to determine the size and location of ESS satisfying technical as well as economical constraints. Now, what are those inputs that need to be given to my algorithm? First is actually network information about the system, network need to be given, and then few cost parameters of this energy storage system need to be given. And what are the expected outcomes? We expect actually optimal operation serving the chosen application, how those objective is being met. For an example, if you are using storage technology to reduce the losses of a distribution system, so then you need to focus that by putting a storage at location A with a magnitude B, how does the loss is going to change with and without storage. So, that is one has to carefully observe. Now, the objectives are according to the network support, that is for example, minimum investment and operation cost, minimum power loss and minimum voltage deviation. So, the example could be anything that you like to reduce the cost, that means you wish to invest less in your network for a couple of years. How do you achieve that? That is known as operational cost management, or you can also optimize the power loss, you can also optimize the voltage deviation. Okay, you can minimize the voltage deviation using storage technologies. Now, there could be n number of constraints that you need to satisfy. One of the important constraint is my power flow constraint. The second important part is the battery operation constraints, and one important point also we need to understand the maximum and minimum range of variables, that is upper and lower limit to anything. For example, if you go for a battery, I may say or we may consider that the battery cannot discharge completely, and I may fix it 20%, 30% as my minimum capacity, and the maximum capacity could be 70% or 8%. So, those are the constraints one need to put, either it is 80% or 90% or the minimum could be 20 or 30. So, depending upon your application and usage, you can fix those constraints. Now, then you have to identify what method I will go for to solve such challenging problem. So, there you can either go for mathematical optimization techniques, you can go for meta heuristic algorithms, you can also approach analytical approach and AL and machine learning technologies. Now, finally, you have to validate of the optimal size and placement results with the real time power networks. So, once you get the simulation outcome, you have to get into the real system, place it and see whether actually it is performing as expected or not. A general distribution planning problem can be formulated as a traditional optimization problem as minimization subject to the following constraints. These functions or equations can be linear or non-linear. So, we know very well how to optimize a problem. However, with battery, those additional constraints related to that device need to be included in my problem formulation. Now, what are those essential parameters? So, mainly we have actually three different parameters that decides my size as well as siting. One is technical parameter, then economical parameters and environmental parameters. So, within technical parameters, the power flow constraints, power loss, and then you have to focus on load curtailments, energy storage system constraints and capabilities, and reverse power flows. Now, in case of economically parameters, that means you need to know what is my investment or replacement cost of a battery, what is the cost of operation and maintenance, what is the cost leading to load curtailment, and what is the challenges, how much money that I can invest, that is budget limitation, and finally arbitrage benefits. Now, looking to the environmental challenges, you can also see to that how your emission can be limited to a particular level. You can talk about resiliency and the amount of land available to you, and then battery disposal and recycling is also one of the important parameters. So, to me those parameters one need to keep in mind before proceeding for storage technology and its optimal solutions. Again I repeat, power flow constraints, power losses, load curtailment strategies, battery constraints, and is there any reverse power flow challenges, investment and replacement cost, operation and maintenance cost, load curtailment cost, arbitrage benefits, emission levels, resiliency and battery disposal and recycling challenges. Now, when you integrate energy storage system, the general power flow algorithms, because if you have a network, either it could be a distribution system or a transmission system, and we need to get the voltage solution of the network at a given point of time. So, you know that different algorithms are available to obtain the voltage solutions in a particular bus and also the power flows. But when you integrate battery, those power flow equations now need to be modeled in a different way, and the problem become non-linear and non-convex. So, that means the general power flow equations which are given by Pij and Pqij, which is the real and reactive power flow between bus I and j, which is known to me, but with integer and binary variables for locations, because of battery the problem become distribution network planning problem and it become MINLP, mixed integer nonlinear programs. So, because of battery integrated to any distribution transmission system, the problem formulation, the power flow problem formulation may take a shape of mixed integer nonlinear programming. And this problem now can be solved, as I told you in the past. It can be solved using heuristics, mathematical programmings, analytical techniques, and AI and ML approaches. Now, considering those methods, whether it is analytical or mathematical or AI or meta heuristic techniques, there are few merits and limitations. Let us see each case one by one. If you talk about analytical methods, the maximum advantage that we have is direct calculation led to easy visualization, highly flexible, but the main challenge is accuracy is low and it is slow in convergence. However, in case of mathematical optimization approach, it is finest solution guarantee, no doubt about it, robust for linear problem, but the computational time dependence on problem dimension, explicit mathematical formulation is equally required. Now, if you go for AI based techniques, it is short convergence time, low computational burden, but sometimes it does not guarantee an optimal solution. Need to have vast database, which is equally difficult. Now, in case of meta heuristic approach, meta heuristic approaches are easy and simply implementation, no gradient calculation needed and ability to avoid local optimum, but it is high randomness. Single algorithm can be trapped in local optimum frequently. Now, let us consider a very simple 33 bus distribution network, IEEE 33 bus distribution network. This is very common in power engineering area, but if you have never used this system, then perhaps you can refer to this. So, what has been, the system 33 bus IEEE will be excluding those PV locations which has been introduced for a better analysis. Now, the IEEE 33 bus system, then we integrate solar panels or solar energy, PV solar energy, and they are integrated at different locations. You can do it anywhere, but these are the 4 locations which has been carried out to intentionally create a scenario where the importance of storage is needed. Now, PV penetration at buses 17, 18, 32 and 33, 17, 18, 32 and 33 with a penetration level of 80% are created, and this system consists of 33 buses and 32 lines, has a voltage of actually 12.66 kV and load size of actually 3.715 megawatt and 2.3 MVAR. So, this is the system that we have considered, and now let us get into the analysis part. Now, we are looking for different solutions. Now, first is actually approximation 1. What approximation we have considered? Nodal voltage magnitudes are assumed close to the rated voltage. The second approximation, which is very common, the small voltage angle difference of a branch ij leading to the approximation of sin theta ij, which is equal to theta ij, and cos theta ij equal to 1. So, the linearized power flow equation P I j and Q I j has been given as below. Now, nodal power balance equations, as you could see, once again my P grid, P V coming out of solar, P D C H, P D G and L C. So, what we have done actually, in case of power, the source of all power that is coming out of my grid, my PV, my battery which has been discharged from the battery power means which is an input to my system, and PDG which is coming from the diesel generator, which must be equal to my actually the demand and the charging of the batteries, the loads are being consumed and also the losses. So, this is the important equation for real power balancing, and similarly you can have a reactive power balancing equation. Now, we can also calculate the P loss as well as Q loss using these two formulas, and then we move to the constraint of the same problem, where energy stored at time t we have already discussed. I am repeating it, E t plus 1 is E t minus delta t P discharge upon efficiency minus P charge multiplied by efficiency, and this is one of my standard constraint. The state of battery, whether discharging or charging, summation will be less than or equal to 1, and the status of initial and final energy level of a battery within 24 hours is considered to be 50%. Now, what is the objective that we are going to solve? Minimize the sum of the power rating cost, energy rating cost, fixed operation and maintenance cost of a lithium ion battery plus grid input cost. So, we are minimizing the cost of energy by putting a battery, so that the overall cost of the system is minimized. So, what we are doing here, we are minimizing the sum of the cost related to power, energy, fixed operation and maintenance of a battery plus grid input cost, means the energy that we have taken from the grid, that cost. So, all summation need to be minimized. So, this is my objective function we have considered to minimize during my optimal process. Now, moving to bit of the parameters, how do you get those parameters when you formulate any problem? So, we try to help you actually by introducing certain variables. Now, the investment cost of lithium ion battery, which is a standard NREL website that we have taken, which is $370 per kilowatt hour, and then fixed operation and maintenance cost we have considered 2%, assumed lifetime which is 10 to 15 years, but we have considered 10 years. Then capital recovery factor, which is R is 7% and lifetime is 10 years, we got it 0.1424, and the discharging and charging period, which is close to 4 hours, and DOD limit is considered to be 20% to 80%. So, what I wanted to highlight here, now you can consider different load patterns. All of you please try to understand, the load pattern of a particular system is keep on changing depending upon different hours of the day as well as different seasons of the day. Means during summer the load pattern is different, during winter the load pattern is different, but when you put a battery technology into your network, you cannot take it back again. So, once it is there, it is there. So, you have to see to that for any load profile depending upon summer, winter or any weather condition, the storage device is really delivering its best. So, we have captured actually 4 characteristics, one is for winter, summer as well as autumn and spring, and we could see that PV irradiation characteristics. So, we know how much power is available during which region. So, we have a load characteristic which is keep on changing based on the weather, and we have a generation characteristic of PV which is keep on changing based on its weather. And finally, we realize that what would be the battery location at 4 different points wherever we have installed the renewable energy PV panels, location 17, 18, 32 and 33. So, we have found that actually the battery of 2.78, 0.46, 4.0, 0.76 megawatt hour, and the power rating of actually 0.7, 0.1 to 1.0, 0.19 can minimize my objective cost. That is how actually one has to identify. So, what you have done actually, perhaps you got bit of the locations and these are my actually siting and these are my sizing, which can help me to minimize the objective function. But when you change the objective function from the cost to loss or some other variation in voltage, then those locations and its rating will again keep on changing. So, depending upon your application requirements, the technology as well as their location and magnitude of the battery will be decided for an efficient deployment of battery storage. Thank you very much for your wonderful patient listening. Before I conclude, I wish to give you following points that you have to remember as a conclusion remarks. The integration of renewable energy resources necessitates the allocation of distributed energy storage to mitigate voltage deviation and defer distribution upgrades. The method used here is mathematical programming, which provides a robust solution, but may require significant computation time for large and complex problems. Uncertainty of loads and PV output and the life cycle of battery will affect the planning of battery energy storage systems. This can be included in your problem formulation. Also, the maximum discharge capacity of the battery gradually declines with its cycle, which can be kept as a future research direction for those who wish to make career in this field. These are the following references you may refer to understand more about understanding the locations and the magnitude of battery that need to be engaged to meet out a particular objective. And with this I conclude my talk. Thank you once again. Thank you.